Okay, in this video, what I would like to do is to get you started by doing a run through of chapter one, an overview of chapter one. So what I'm going to do is I'm going to come in and open up the ebook. So here we are, chapter one. Chapter one has 6 sections in it. The study of chemistry, classification of matter, scientific measurement, the properties of matter, uncertainty in measurement, and using units in problem solving problems. So the first 3 sections are really very, very simple introductions. Um, when you get down to uncertainty in measurement and using units and solving problems, it's a little bit more advanced and more detailed. So one of the things that you'll notice as you go through this chapter is that the first few sections are what we would call descriptive discussions of chemistry. So they're giving you some terminologies, an introduction to things. As we get to the end of the chapter, we will see that we're moving into more detailed analysis of how we study chemistry. So I'm just going to give you an overview here. This is not meant to be a replacement for reading the textbook or solving the problems. In future videos, I'll go through and give you some specific examples of problem solving. But for this, we're just looking at an introduction. So the study of chemistry, now, why would we want to study chemistry? Chemistry is important in material science. So all of the technology that you're using to watch this video is developed partially on what we call material science, silicon, purifying silicon and crystallizing it so that we can make computer chips, lithium ion batteries, which involve the refinement of the earth, taking materials from the earth out of the ground, which required geologists to figure out what parts of the earth do we look for these particular materials. They don't exist everywhere in the earth's crust. Refining those materials into their pure elements or their pure compounds, and then working with them in factories to develop the new materials. So lithium ion batteries are a good example of that. So one aspect is material science. Another is pharmaceutical chemistry. So these days, if you watch television or you watch YouTube commercials, you'll see that a good portion of the commercials out there are for pharmaceuticals. So drugs that are used to develop, improve health or bring back health. Or maintain health, those sorts of things. So those are aspects. Chemistry of food chemistry, of course, is important. All of the processed foods that we eat involve the purification, refinement, synthesis of new types of compounds that keep foods fresh or keep foods, provide nutrients in foods, those sorts of things. So, of course, you see chemistry at work all the time. You may not be aware of it when you turn on a flame in your kitchen. That's a chemical reaction occurring. It's called combustion. When you see a piece of metal outside, so for example, you look out and you see that the rails on the train are rusting, that's a chemical process. Rusting is called oxidation. If you've used Alka-Seltzer, that's a chemical reaction. And cooking, like baking specifically, is a very good example of chemistry. Okay, so we use in chemistry what's called the scientific method. I'm not going to go through this in great detail, but you should look through here and see if you can figure out on your own through this discussion in here the scientific method. We don't expect you to be experts in the scientific method. We primarily, in the natural sciences, we learn the scientific method through practice. But there are some terms you should be aware of: the scientific method, what a law is, what a hypothesis is, and what a theory is. What do molecules look like? Well, it's an interesting question. What do molecules look like? They're very, very small, so we do have technologies that can give us an idea of what they would look like if we could see them. We can determine what their geometric shapes are. We can determine their extensions in space, how large they are. But in fact, molecules, because they're so small, we cannot see them with our eyes. So it's not even an appropriate question to say what they look like, but we can talk about how they behave and how their sizes and their structures affect how they behave. And then we will be a little bit more loose with our language and talk about what they look like. But in fact, you can't actually see a molecule. We do develop what are called molecular model kits. We don't use these too much in general chemistry. If you go into organic chemistry, the molecular model kits are essential to your understanding of the spatial relationships of atoms. So these kits often have a color code. So a white ball would be hydrogen, for example. A black ball would be the carbon atom. A blue ball would be the nitrogen atom, and oxygen would be red. And we would link those little balls together, those atoms together, by using little linkages. So you see here what's called the ball and stick figure with the red oxygen in the center, surrounded by two white balls, which are hydrogen atoms, and that would represent H2O, or the water molecule. There are also space-filling models that are used. Those are less common. You don't see those as often. Those are a little more realistic in terms of what molecules, quote, look like in space. And then at the end of this section is a flowchart of the scientific method. So that's section 1. I'm going to move on now to section 2. And section 2 is a little bit of information about how we classify matter. This is an important aspect of chemistry, and one which you'll work in the laboratory when you take a future general chemistry class. So states of matter, we are familiar with most of those: solid, liquid, and gas. In a solid, the atoms are very close together. They're packed together. They're rigidly held together. In a liquid, which is in the center of this figure 1.4, the molecules are also stacked pretty close to each other, but they're able to move freely with respect to each other. They flow. So if you take some water, some liquid water, and rotate the container, in this case it's a flask, you can see it move around. An ice cube, on the other hand, the actual object might move, but the positions of the atoms relative to each other would not move. And then a gas, of course we know gases will fill up the entire container, and they tend to be very widely spaced molecules or widely spaced atoms. So those are three little illustration of that. Here's an example of all three states of matter with water. There's a little burner down at the bottom using natural gas and burning that natural gas to boil water. So there's liquid water. It's boiling, so it's turning into what's called steam. So that's gaseous water. And then at the top there, you see an ice cube, a bunch of ice cubes, in fact. So there's the solid states. So all three states of water exist simultaneously in that picture. Okay. So here are a couple of pictures. This is figure 1.6 showing you isolated atoms. That's in figure A. So those are individual atoms of an element. And we'll talk more about elements as we go through the periodic table. In slide B here, you see molecules. So notice the molecules, they're all same color. So that means they're all the same element. But in this case, there are two atoms stuck together. So that we call, when we have atoms stuck together like that, we call them molecules. So the first picture is showing you individual atoms. The second one is showing you molecules. Those are both of elements, because there's only one type of atom in each of those pictures. But you move on to C. In figure C, those are molecules because there's more than one atoms attached to each other. But notice there's two different colors used. So each molecule has two different colors. So two types of atoms or two types of elements. So those are what are called compounds. When you have two or more elements stuck together like that, we call those compounds. And then over on the right, if picture D, if you take a look at that, they've essentially combined all of them together. The individual yellow ones or orange ones are atoms. That's an element. The individual blue ones are two atoms stuck together, so those are molecules. And then you've got the compounds over there, which have the purple one in the middle and then the green ones surrounding them. Two different elements. Those are compounds. Okay, so again, you want to read through here. There's a discussion here about mixtures, about different types of mixtures. Again, I'll let you read through there to figure that out. And then there's a nice classification system shown here in this flowchart about how you identify different forms of matter, taking a mixture and then separating it into what are called compounds and elements. And it takes a chemical process to turn compounds into elements, whereas it only takes physical processes like using magnetism to separate mixtures. Okay, so that's section 2. The next section is the scientific measurement idea. So we will make measurements in the laboratory when you take the laboratory component of Chem 1100 and 1200 if you go on to take that. We don't really have a lab component of this course, so we're really just going to talk a little bit about what it's like to work in the lab. These are some common pieces of instrumentation that we use in the laboratory. These are measurement devices. They're all glass or plastic. One's called a volumetric flask. Next to that's called a graduated cylinder. The next one is called a pipette. And the last one's called a burette. So these are ways to measure volumes of liquids. These are designed to measure. So just like a measuring cup in the kitchen, this is a device we would use to measure a certain volume of a liquid. We use what in chemistry what's called the SI base units. Almost all chemists use SI base units. And so table 1.2 gives you a list of the base units. The base unit for length in the SI system is called the meter, and the abbreviation of the meter is a lowercase m. For mass, it's the kilogram, and the symbol for that is kg, lowercase both k, lowercase g. For time, it's the second, and the abbreviation for second is s. For electric current, which we won't use too much in general chemistry, there's one topic where it gets covered in the second semester. It's called the ampere, and the symbol for that is a capital A. The abbreviation is a capital A. The temperature unit that we typically use is Kelvin, and the symbol for Kelvin is a capital K. We'll see in the next section that there's some temperature conversions that involve the Kelvin. The amount of substance, this will be important later in the course, is called the mole, M-O-L-E, and the abbreviation is not much of an abbreviation. We just take off the last letter E, and it's M-O-L, the mole. And this is almost never used in general chemistry, very rarely used in physics even. Luminous intensity, that's the intensity of light, is called the candela, candles, and the abbreviation for that is CD. So what happens in natural sciences is that numbers can be very, very large, or they can be very, very small. So for example, the size of an atom is around 10 to the minus 10 meters. 0.000 with 9 zeros in meters. So very, very small, or they can be very, very large. So for example, this pen that I'm holding up here has some ink in there. The number of molecules in there is somewhere around 10 to the 21, 1 followed by 21 zeros. It's a very large number. So we have large and small numbers. So we have different ways for dealing with that. One is through what's called exponential notation. So here are some powers of 10 listed here in table 1.3. The top one, tera, with a capital T, is 1 times 10 to the 12th. So that prefix is a way of representing a large number. So for example, if we have a teragram, that would be a way of saying 1 times 10 to the 12th grams. So the unit is gram. That's a measurement of mass. The prefix is tera. That's a measurement of powers of 10. So if we have 1 times 10 to the 12th teragrams, that would be, or if we have 1 times 10 to the 12th grams, that would be 1 teragram. A small number, very small number, would be pico. So if we have 1 picogram, that would be 1 times 10 to the minus 12 grams. So that would be 0.000 with 11 zeros and then grams. That would be a very, very small mass. Okay, so those are the prefixes. Generally, I don't like people, or I don't recommend to people that they memorize a whole lot. One of the reasons I went into chemistry is I don't like to memorize lots of pieces of information. However, the prefixes are very useful if you memorize them. So I would recommend that in table 1.3 you do try to put some effort into memorizing them. Use flashcards. Just go buy some cheap flashcards from Dollar Tree or from Target and just memorize these things. It's not going to be the end of the world if you don't, but it's a nice piece of information to have if you're going to continue taking science courses. If this is your last science course or you're only going to take one more, it's probably not a big issue. But if you plan on doing engineering or you plan on being a bio major, it makes your life easier if you know certain pieces of information. So the prefixes for the SI units are an example of those. There are other SI units out there. I'm not going to suggest that you memorize those as well. These are the most common ones here, going from tera, which is 10 to the 12th, all the way down to pico, which is 10 to the minus 12th. So notice that table is big numbers and also small numbers. So mass is something that we measure and we study quite a bit. We'll see that chapter 3 is pretty much all dedicated to the measurement and study of mass. So an example here is 1 kilogram is 1,000 grams, 1 times 10 to the 3 grams. So notice there's 3 different ways that those numbers are being represented to us. The first one is using a prefix, kilo. The second one is using what we will call decimal notation. 1,000 is a decimal number, so 1,000 grams. And then on the right is 1 times 10 to the 3 grams. That's another way of representing it, and that's called scientific notation. Then this section goes into temperature conversions, the conversion between degrees Celsius and Kelvin. You are probably familiar, or at least more familiar with Celsius. It used to be called the centigrade scale, and the Celsius scale is based on the freezing point and boiling point of water. Water freezes by definition at 0 degrees C under atmospheric pressure, and it boils under atmospheric pressure at 100 degrees C. That's actually why it's called the centigrade scale, in addition to Celsius. Centa meaning powers of 10, so 0 and 100. However, what we'll see when we go through discussions of gases and discussions of energy is that the Kelvin scale is actually a much better system of temperature measurement or temperature calculations. So the Kelvin temperature scale is given here. Not in great discussion, just showing you how to do the conversion. And so go through these problems in terms of converting between Celsius and Kelvin. And then you see your first sample problem here, 1.1. As I said in the earlier videos and in the syllabus, make sure that you do the sample problems, make sure that you do the practice problems. The answers are shown here. I recommend getting a composition book, again from Dollar Tree, something like that. Don't spend more than $1, and just do all your problems in a composition book or a binder or something like that. Okay. And then there is another sample problem going from Celsius and Fahrenheit. Now, we don't do a lot of Fahrenheit calculations in general chemistry, but I did want to put this in the syllabus and have you work on it a little bit, because if you're going to go into the medical field, it becomes an issue that going from Celsius to Fahrenheit is something that occurs. In the United States, we generally talk about temperature in terms of Fahrenheit values. So for example, if someone is sick, their temperature might be over 100. Well, in the Celsius scale, a temperature of over 100 is actually a temperature around 40 degrees Celsius. So we need to be able to do those conversions as well. So try your sample problems. There's a discussion here about derived units. So we talked about earlier, I'm going to go back to show you what are called base SI units. So those are those 7 right there. Derived units are just units that are combinations of these base units. So for example, volume is length. Here's a cube in figure 1.10. Volume is length cubed. So it's, for example, the depth times the height times the width of this cube. That's a derived unit because you're taking a length unit and multiplying it by another length unit and then multiplying it by a third length unit to give you volume. You're deriving the volume unit from the length unit, which is a base unit. Okay. And then, of course, there's sample problems here. Density is something that we need to be familiar with. So here's a little discussion about density. So you want to go through that. And why are units so important? This is an interesting aspect of units. The Mars Climate Orbiter, a little story here. My story might be a little bit different from the one listed here in the textbook, but essentially it's the same idea, which is that NASA spent around $150 million to launch an explorer over to Mars to go into orbit around Mars, and it essentially burned up in the atmosphere of Mars, didn't go into proper orbit. And the reason was that engineers were using a different set of units than the scientists were. So a project like that involves the cooperation of scientists and engineers, and they were using a different unit system. One was using what's called the imperial unit system. You're familiar with that as inches, feet, and yards. And the other one, the other scientists were using SI units, for example, meters or kilograms, and they didn't cooperate quite correctly. And what happened was the device, the orbiter, when it tried to do its final burn to go into orbit, proper orbit around Mars, it didn't have the right number because it was using a different system than the engineers had designed it to use, so it burned up in the atmosphere. So these things do happen. We call that a cautionary tale about taking things importantly. The details are important when we do these types of calculations. And so at the end of this section are the checkpoints on the scientific method, scientific measurement, and so you'll want to go through those checkpoints as well. The next section, again, is a more descriptive discussion of chemical and physical properties. So I, again, encourage you to read through these, try the sample problems, try the practice problems, and try the checkpoints. But I'm not going to spend much time on there. This is a chemistry course, so it is somewhat important to know the difference between chemical and physical properties. So read through this section, and I'll give you some details on that. The next section is uncertainty in measurement, and this is something you'll see in ALEKS. There's going to be some problems in ALEKS under uncertainty when we measure things. One of the things that makes this course a little bit difficult is that you're not actually going to have a lab component, so you're not actually doing measurements. So the advantage of that is that you don't have the time commitment, and you don't have to write lab reports. In the next course you will, but the disadvantage is you don't get the hands-on experience here. So when we talk about significant figures, this is going to be from a purely theoretical perspective. But notice this figure 1.11, where they have a flash drive there, 64 gigabyte, is that they're measuring in centimeters on the top, but they're also measuring in centimeters in the bottom. So they're measuring the length. But notice the one on the bottom has more lines on it that are more closely spaced to each other. So what we're talking about here is how precisely we can make a measurement and how accurately we can make a measurement of length. So if you look at the one at the bottom, because you have those extra lines that are more closely spaced, we're going to have a little bit of better measurement right there. So we generally talk about the quality of a measurement in two ways. One is through accuracy, which is this idea of how close are we to the real value. We know that something has a size, we see it with our eyes, but how close can we get to that correct value? And we call that accuracy. The other issue is what's called precision, which is if I measured it more than once, and how close would I get to the same answer both times? An example of this is, suppose you had a bunch of marbles in a jar, and you tried to count them just by looking at them. And so you estimated the first time as 50, and then the next day you did it again, and you looked and you said, well, now I think it's around 70. You would have very different numbers in those cases. So our measurements are not very precise. To be more precise, what we would do is we would, we would pour them out and actually count them individually. And then we could, if we did that 3 times, we could get a very precise measurement of what's going on. You get the same answer every time, essentially. So what we're going to show, or what the textbook shows you here, and what ALEKS shows you, and what I discuss, is this idea of dealing with what we call significant figures. So read this section on significant figures. You'll see that there are 5 rules here. You want to practice those rules. You want to memorize these rules as well. And then based on those rules, you're going to do the sample problems, and you're going to do the calculations, and you're going to do the sample problems and the practice problems. And notice there's a few practice and sample problems here, more than in the other sections, and that's because this is a real skill you're developing here. Just like when you were younger and you tried to learn how to do long division, you had to do lots of practice to get it down. Same thing here. You're going to do lots of practice on this to get this down. Okay. And then there are checkpoints as well. So notice this one has 4 calculation checkpoints there. Okay, so that's more detail. There's more detail in this particular section, and you'll see that as we move along, that's what's going to be essentially this course, is more details, more details. The last section here is using units and solving problems. This is what we would call dimensional analysis, dimensional analysis with an A, or factor label method. This is a method of learning how to do problems. So conversion factors. So for example, 1 inch is equal, it's actually the inch is defined by the centimeter, meaning that 1 inch is by definition 2.54 centimeters. Imperial units are now defined based on SI units. And so the inch is 2.54 centimeters. So we can do problems by creating what are called conversion factors or ratios, divisions. 1 inch divided by 2.54 centimeters, or 2.54 centimeters divided by an inch. So here's an example of a conversion. If we have 12 inches, how many centimeters is that? 12.00 inches times 2.54 centimeters divided by 1 inch. What happens is the inches divide out. They cancel, if you want to use that term, meaning an inch divided by an inch is just 1. The inches divide out. And so just like 2 divided by 2 is equal to 1, an inch divided by an inch is also equal to 1. So a unit divided by the same unit is 1. So by doing this, an inch times a centimeter divided by an inch is a centimeter. And that's called dimensional analysis. And that's what you want to get skilled at. That's another skill you want to learn out of this course through lots and lots of practice. Okay. Here's a little bit more about tracking units through dimensional analysis. And then here's an example, sample problem 1.8, practice problem, sample problem 1.9, practice problems, and then some checkpoints. So again, the last 2 sections are very heavy compared to the first 4 sections. Lots of practice in there. And then after you've gotten through those sections and done those practice problems and sample problems, that's when you want to go through and start working on more problems, okay? So more problems would be right here, section 1.1, 1.2, 1.3, 1.4, 1.5, and then 1.6. The problems at the end of the chapter that I would suggest you work on are the ones that are listed in the syllabus. So bring up that syllabus out of Blackboard, take a look at that, and that'll tell you which ones to work on. Of course, you're also doing the ALEKS problems, right? So this is going to start getting time consuming pretty quickly. And what I would say at the beginning of this course is some of you coming into this course are probably pretty advanced, and this is not going to be a problem for you to do these problems. You may have learned them in high school or even middle school, depending on where you went to school. However, for some of you, this is going to be a challenge, and sometimes the most difficult part of doing problems is the beginning. The simplest problems can actually be the hardest ones because you don't understand the concept. Once you understand the concept and you've practiced it, then doing more advanced problems can actually get easier, and I've seen that with many students. So don't get put down. Don't feel bad about yourself if you're having difficulties with those first problems in section 5 and section 6. You'll get better at it if you practice. Believe me, these things can be figured out by all of us. So that pretty much ends the discussion of chapter 1. I'll have also one for chapter 2 coming up in the next week, and then another one for chapter 3. Chapter 2 and 3 are a little bit lengthier chapters, so I may break those up into 2 sections. But this is a good intro into chapter 1. So good luck. Remember, read, do problems, be organized, and don't be afraid to reach out for help if you need it.